course, IoT is all about sensors. And regardless of whether they're doing the CO2 levels or taking a look at a camera, they're going to be analyzed in some fashion, oftentimes with machine learning. Could you tell us, Kim, a little bit about how you see smart sensor technology and where it fits with respect to a designer's need to get analog data out into their application?
Sure, Bill. So, nowadays systems are being required, today's market economy applications. They're required to be more complex. I mean, smarter cameras, smarter thermostats, smarter devices that make our life more convenient. And this starts with having the ability to sense the environment or sense surroundings, make action from that, understand what information they're seeing, and then actuate the specific action for that system, and then provide the the resulting outcome. Now, sensor data is starting to get digitized. It's starting to require more compute, and what we're seeing from a sophistication standpoint, we're trying, at least from an Infineon standpoint, we're seeing the complexity of even in very simple example with robotics, right? We're trying to get machines to be more human interacting, and that requires the smarter sensors, from having smarter eyes, smarter ears, smarter noses, if you will, and smarter touch sensing as well. And this is basically real world data that is being acquired by the sensor and then processed internally in order to make a decision on what to do.
Okay, well, we're going to get to some of Infineon's sensors a little bit later in more detail. But in general, sensors have typically started out with analog inputs, and the microcontrollers then had to do the analysis. How has that changed at this point? What kind of interface do we have on these smart sensors, and how much actual computation are they doing?
Yeah, I mean, traditional sensors used to be a very simple GPIO analog output, and even to some extent a digital control line as an output that would signal yes or no. Nowadays, we see sensors already having I2C, I3C interfaces, SPI interfaces for more data, for more speed, and the compute, from a very simple 8-bit micro is being, depending on the amount of data that the sensor is bringing in, could require something the size of an M4 ARM level compute, to even higher, depending on the amount of data that's being accumulated and the resolution that the sensor has. Are
you seeing more machine learning being incorporated actually within the sensor module?
The machine learning, that it will come, yes. That a lot of the actual machine learning and the digital signal processing being done traditionally has been on the compute side itself, but there is a shift that we see that is going to be in the sensor itself. It's all a trade-off, and how much of this compute do we put into the sensor versus how much do we keep off on the actual compute engine, which is the MCU or the SoC. And there is a slow shift on taking a lot of the the FFT, the fundamental math and the DSP part of it into the sensor.
Infineon has the XENSIV line of sensors. Could you talk about sort of the whole family of these things first?
Again, as I mentioned, we're trying to mimic human senses with our XENSIV sensor family: smart eyes, smart feel, smart nose, smart ears. And it starts with going through this human-like experience of taking that input in the outside world and converting it to digital signals that we can process and make outcomes out of. First example would be a very simple MEMS microphone where we have very good MEMS technology with high SNR as well as high performance that we can use for better listening, not just the MEMS microphones that are out in the market today, but even more performance and higher specifications that allow not just premium recording, but being able to authenticate voice properly, being able to identify an acoustic event and being able to process that, whether it's, let's say, glass break, gunshot, EMS sirens, things like that. They are being getting more in demand, where we're seeing accurate audio processing being necessary to realize this type of sensing capability to take action on, let's say, emergency services, or as an example.
You also have radar, and we have a little demo. Could you talk a little bit about what's happening here?
Yeah, so radar is another technology that we have inherited from our automotive technologies in the 77 gigahertz range, but we have 24 gigahertz and 60 gigahertz radar. And what we're doing with that is mimicking a smart eyes concept, where we're looking at a field of view where like a lenses camera, where the sensor is actually looking at images or reflections of people without actually having the resolution to identify the person. So you can put this behind a plastic or some kind of enclosure that is really hidden and aesthetic as far as the implementation. And in this particular demo, what we're seeing is that it's put behind, let's say, a smart monitor, or behind a monitor where we're looking at where people are in a room. It's basically a tracking and zoning type of implementation, where when people walking into the room, passing by or sitting down, they have the sensor knows where they are in a room. They can optimize the viewing experience. For digital signage, for example, they can change the content of what the person's seeing depending on if they've stopped in front of the signage, and the radar sensor detects that, so that oh, this caught my eye. I'm going to stay here for another second to see what was that, what was that was showing on the signage. Or at home, like a smart TV, where you have people in the living room or in different areas, and with the understanding of where people are in a room, you can actually audio beamform and specifically provide the user, as they're sitting wherever they're sitting in the room, a more optimal viewing experience and hearing experience.
Okay, so how does the time of flight support that you have differ from the radar?
The time of flight support is very similar in the smart eyes concept, except it does have a lens. It has more resolution, up to a VGA resolution. So it's basically a camera with depth perception, except it's not where cameras are today with like 4K and soon to be 8K level resolution. But it's enough to be able to determine facial recognition, facial authentication, being able to determine profiles from a 3D standpoint on objects that are within front of the camera. It's more of mapping a room using this type of technology to do SLAM applications, for example, as well as like I said, authentication examples.
Now you have a very accurate pressure sensor. Can you tell us about that and why it's different?
Yeah, the pressure sensor is basically based on our MEMS technology with very superior MEMS processing, and the microphone technology that we use. We've basically applied this to a pressure sensor, which is basically when you break it down, a microphone technology. But what's nice about the pressure sensor is, in this particular family of pressure sensor, it's more accurate and the most accurate in the market today in the form factor that it's in. Very small form factor. It's deployed in wearables, as well as many other things, where the accuracy is such that we can go into a room, climb a set of stairs, and you can measure the actual movement from that granularity for each step that's being taken, which is pretty nice.
Mm-hmm. You also have an air quality sensor that you have a demo on.
Yeah, so the air quality sensor is measuring CO2. CO2 is very popular these days in terms of understanding the CO2 content around you, because when you're in a room and you get a little tired, a little sleepy, it may be just because the CO2 content is in the room is just increasing. So what do? You may want to open the window, turn on the ventilation, or just leave the room when you know that's unhealthy air that you're breathing. So what we're looking at here is a user interface that is just looking at the CO2 levels of the sensor here. And the sensor is basically a very small 1 inch by 1 inch module that has a traffic light of green, yellow, and red, whereas green obviously is where good CO2 content, acceptable CO2 content is being measured. As you can see, while I'm kind of venting, wave my hand at the sensor, just getting fresh air into it, you can see the sensor readings go down in terms of CO2 levels, in terms of safety. You can see the level's still good, no health risk. As I blow into it with my breath and add CO2 in there, you'll see this go up and spike up a little. And we're measuring it over a certain few second interval in order to get refresh rates. And you could see in real time, now that I've blown into it, I've increased it slightly, and it can be measured. So what's nice about it is that it's a kind of a personal like device, very portable, uses USB power or a battery, and you can have it in your person, where you go into any room, any restaurant, and look at the air quality in terms of CO2 and determine whether or not it's um, the facility should open the windows, turn on the AC, vent the room, whatever the case is, in order to get fresh air back into the environment where you're at. So in this particular case, in the GUI, with the breath of CO2 that I blew into it, you can see the momentary increase that you see there. And since I'm now just away from this sensor, it's getting back to a level that is going to be acceptable once it refreshes further.
Excellent. So we've covered quite a bit of area in terms of sensors. How do you see these things being integrated together? Because they all do sense different areas.
Yeah, a lot of demand we see now, especially with smart homes, smart buildings, is understanding population in a certain area, understanding where people are, or understanding what's going on, the situation of a particular area. And in order to do this, we need to monitor not just with cameras, but it could be with microphones, it can be with other sensors like CO2 sensors. The more people that are in a room, the CO2 content is going to increase. The more the radar, for example, can be very complementary to a camera, whereas power savings is a big example of something that we're also very much trying to improve. A camera, a surveillance camera, for example, has obviously a high resolution camera. It has Wi-Fi and wireless capabilities that take the image of what you're seeing into like a mobile device, into the cloud, onto a mobile device. And from there, you're able to determine, okay, is somebody in the backyard a threat, or what is that what I'm seeing in the backyard? Um, Radar can be a very simple monitor for that movement, where it's monitoring a person, monitoring just a person, and not something else that's triggering the sensor that will turn on the camera, such as a wind blowing the trees in the background, or sunlight that's fading in the back, that automatically turns on the passive sensor that's there, and then that enablement of that sensor is then turning on the camera, the SoC, the wireless, and then you're consuming more power. You're putting maybe data on the through the Wi-Fi and the bandwidth that you're hogging, sending information that you're not interested in looking at, is then just more of a waste of energy, as well as bandwidth for something that maybe you don't want to see, or it's not really important. the intelligent sensor like a radar sensor would be able, and maybe match that and fuse that with a microphone, to fuse these sensors together to make even a more intelligent understanding of human presence in an area where, let's say, it's detecting that presence in a low enough power where, once it detects it, it turns on the rest of the system to show that movement on a mobile phone. So enabling the SoC, camera electronics, as well as the wireless connectivity.
Very good. Well, thank you for discussing smart sensors and filling us in on Infineon's platforms.